Imagine you are tasked with designing the microscopic silicon chip inside the smartphone you're holding right now. You've got literally billions of microscopic transistors to arrange, and you need to find the absolute perfect optimal layout.
Right, which is no small feat. I mean, the goal is to maximize processing speed, make sure it doesn't just melt the phone's battery, and, fit it all into an impossibly small physical footprint.
Exactly. And you can't just check every possible layout because, well, analyzing billions of components in every single configuration would take longer than the lifespan of the universe.
Yeah, way longer. So the big question is, how do you find the absolute best answer without checking all the alternatives?
Right. And today we are exploring a really comprehensive 2026 presentation by a researcher known as Luck036. It's titled Fundamentals of Mathematical Programming and Convex Optimization. We're basically getting into the mathematical sorcery that makes our entire digital reality possible.
Yeah, and the core mission of this deep dive is to explore how engineers and algorithms map out these impossibly massive decisions. We're looking at the specific mechanisms they use to isolate the absolute best choice out of billions of variables.
It's just wild. The mathematical trickery required to solve problems that look completely, unsolvable on paper.
It really is.
Okay, let's unpack this. Because mathematical programming isn't just writing Python code, it's the science of optimizing an objective like minimizing cost or maximizing power while navigating very strict constraints.
Exactly. You have an objective function and you have your hard limits, like your inequality constraints. But setting up those equations is actually kind of the easy part.
Yeah, the real nightmare begins because the physical world rarely gives us clean, easy equations. The real world is overwhelmingly what mathematicians call non-convex.
Which is really the central tension of the presentation. A non-convex problem is just notoriously difficult to solve globally.
Right.
Like, you might run an algorithm and find a really good answer, maybe a highly efficient layout for your chip, but you have zero mathematical certainty that you found the absolute best answer.
Because there might be a layout that uses, I don't know, half the power just hiding in a blind spot of your equations.
Precisely. And because the real world is so messy, engineers have to rely on a specific theoretical framework that they try to force these real-world problems into. And that framework is convex optimization.
I always picture non-convex optimization like you are wandering through a massive foggy mountain range trying to find the lowest possible point.
Oh, that's a good way to look at it.
Yeah, so you walk downhill until the terrain starts sloping back up, you've found a valley. And mathematically that's a local minimum. But because of the fog, you have absolutely no idea if there's a much deeper valley 3 miles to the west. You're just stuck in the one you found.
Right. But convex optimization entirely removes the fog in the mountains. A problem is strictly convex if the objective function and all inequality constraints are convex functions, and the equality constraints are strictly linear.
Okay, so geometrically, what does that actually look like?
Well, geometrically, if you draw a line segment between any two valid points in a convex space, that entire line stays inside the valid space.
Oh, okay. So instead of a foggy mountain range, convex optimization is like standing in a giant, perfectly smooth parabolic bowl. If you drop a marble anywhere in that bowl, it's always going to roll to the absolute bottom.
What's fascinating here is the absolute guarantee the geometry gives you. I mean, in convex optimization, any local minimum is mathematically guaranteed to be the global minimum.
Because there's only one bottom of the bowl.
Exactly. There's only one bottom. Furthermore, these problems are solvable in polynomial time, meaning computers can find that bottom efficiently, scaling pretty reasonably as the problem gets bigger.
Okay, but to prove the marble is actually at the bottom of the bowl, the source material dives into something called duality and the KKT conditions.
Yes, duality is huge here.
And my understanding is that duality relies on the Lagrangian, which it kind of feels like a way of combining the goal of the game with the rules of the game.
That is essentially the functional purpose of the Lagrangian, yeah. It takes your main objective function and folds all of your constraints into it by assigning a penalty, which we call a dual variable, to each constraint.
So instead of checking constraints separately, the Lagrangian forces the algorithm to pay a mathematical price every time it pushes against a limit.
Right. Which brings us to the KKT conditions Karush-Kuhn-Tucker. The presentation lists these as the ultimate proof of optimality. If you satisfy them, you've completely solved the problem.
But let's break them down because just reading them off a slide can be, well, really dense. The first two are primal feasibility and dual feasibility.
So primal feasibility just means your proposed solution actually obeys the original physical rules you set. Basically, you didn't break the laws of physics.
Always a good start. And dual feasibility.
Dual feasibility means those penalty values we just talked about, the dual variables, they have to be strictly non-negative. You can't be rewarded for breaking a rule.
Okay, got it. The third one is complementary slackness, which honestly sounds completely contradictory. What does slackness mean in an optimization equation?
Think of a constraint as a physical rope tying your algorithm back from an area it wants to explore. If the algorithm is pulling as hard as it can against that rope, meaning the constraint is acting as an active bottleneck, the penalty is high.
Oh, I see.
But if the algorithm naturally finds an optimal spot far away from that constraint, it isn't pulling the rope at all. The rope is slack.
Mm.
So complementary slackness mathematically dictates that if a constraint isn't acting as a bottleneck, its associated penalty drops to absolute zero.
Okay, so it's only penalized if it's hitting the wall. And the final condition is stationarity.
Right. And stationarity proves that the forces are completely balanced. There is no direction you can mathematically move to improve your objective without instantly violating a constraint or incurring a massive penalty.
Wow.
Yeah, if a convex problem satisfies these KKT conditions, you have unequivocally found the global minimum.
I mean, mathematically, dropping a marble in a perfectly smooth bowl is a beautiful theoretical trick. But a piece of paper can't build a microchip. And as we established, the real world doesn't look like a bowl. It looks like a foggy mountain range.
Sure.
So do engineers just give up when the physical reality is non-convex?
Not at all. They use a process called convexification. They basically mathematically warp the space to force the mountain into a bowl.
Force the mountain into a bowl. That sounds intense.
It is, and the core mechanism for this is applying monotonic transformations. A monotonic transformation fundamentally changes the values of the variables, but it strictly preserves the ordering of the solutions.
Wait. If I'm changing the variables and warping the mathematical space to make the math easier for myself, am I still actually solving the original problem? Or am I just moving the goalposts to invent a game I can win?
That's a great question. Because the transformation is monotonic, the map scales reliably. If design A was better than design B before you warp the space, design A will still be better than design B after the space is warped.
Okay, I'm tracking with you.
So when you find the absolute bottom of your new artificial bowl, that specific point maps perfectly back to the deepest valley in your original messy mountain range.
That is brilliant, but how does an engineer actually mechanically warp the space?
Well, let's look at a perspective transformation, which is used heavily in fractional programming.
Hmm.
Say you're trying to minimize a ratio, like manufacturing cost divided by component durability.
Ratios are notoriously non-convex, right?
Exactly. If you graph a complex ratio, it creates a messy, undulating 2D curve with multiple valleys. But through a perspective transformation, you essentially divide the variables by a new scalar, which conceptually adds a dimension.
Okay.
You view that undulating 2D curve from a 3D perspective. Suddenly, from that new higher dimensional angle, the geometry naturally forms a perfectly convex, solvable space.
So you basically step out of the 2D fog to look at the mountain from above, and from the sky, it looks like a bowl.
Exactly. It's all about perspective. Another major transformation is geometric programming, or GP engineers frequently work with equations called polynomials.
Polynomials. What are those?
They're just sums of variables raised to various powers multiplied together. Polynomials model physical realities like power dissipation perfectly, but they are inherently non-convex.
So how do you fix them?
Well, if you apply a specific logarithmic transformation, basically taking the log of the variables and exponentiating the sums, that messy polynomial instantly becomes a strictly convex function.
It's almost like a mathematical translation layer.
It really is.
Now, the presentation also mentions quasi-convex programming. This implies a space that isn't quite a perfect bowl, but close enough.
Yeah, close enough to solve. In a quasi-convex problem, the overall 3D shape might be distorted, but if you were to slice it horizontally, every single cross-section, which is known as the sublevel set, is perfectly convex.
Okay, and why does that matter?
Because the cross-sections are reliable, you don't need complex calculus to find the bottom. Engineers can just use the bisection method.
Which is basically how you look up a word in a physical dictionary, right?
Yeah.
You open to the middle. Is your word in the first half or the second half? It's in the second half. So you discard the entire first half, open to the middle of what's left, and just repeat.
That's a perfect analogy. The bisection method does exactly that with the algorithm search space. It repeatedly cuts the valid area in half until it zeroes in on the optimal cross-section.
Wow.
Yeah, and the final convexification tool the presentation highlights is linear matrix inequalities, or LMIs.
Okay, now we are getting into some heavy jargon. The text describes LMIs as dealing with positive semi-definite constraints. What does that actually mean mechanically?
So instead of looking at single variables, LMIs look at matrices grids of numbers representing complex multivariable systems. A positive semi-definite matrix essentially means that the energy in that system is always positive or zero.
Meaning it isn't creating energy out of nowhere.
Exactly, which mathematically translates to stability. The true power of LMIs is composability.
Composability.
Yeah, like if you have 50 different complex stability requirements for a control system, you don't have to solve them one by one. You can mathematically stack them all into one giant unified LMI, and the entire block remains convex and solvable.
So we have these incredible mechanisms, perspective transformations, log sum X translations, LMIs. We've successfully bent the physical mountain range into a pristine mathematical bowl.
We have.
But how do we actually program a computer to find the bottom of that bowl when there are millions of interwoven variables?
Well, this is where the algorithms take over from the theory. The presentation marks a historic breakthrough from 1976, the ellipsoid method.
The ellipsoid method.
Yeah. This was the specific algorithmic mechanism used to prove that linear programming could be solved efficiently in polynomial time.
So how does the ellipsoid engine actually run?
It works by maintaining a mathematical containment field, an ellipsoid, which is just a stretched out multidimensional sphere. The algorithm ensures that this initial ellipsoid is large enough that it absolutely must contain the optimal solution somewhere inside it.
Okay.
It then queries an oracle at the exact geometric center of that ellipsoid.
Here's where it gets really interesting, because calling it an oracle sounds like, I don't know, ancient mythology. But mechanically, it plays exactly like the game Guess Who.
Oh, I like that comparison.
Right. You have a board full of faces. You ask a question like, does your person have glasses? The answer is no. Boom. You draw a line across the board, flip down half the faces, and completely eliminate half your search space in one move.
That is the exact mechanism. You feed the center point to the mathematical oracle, and the oracle returns a cut.
Like cut.
Right, a separating hyperplane. The oracle evaluates the center point and mathematically guarantees the absolute best solution is definitely not on this side of the line.
And the algorithm just instantly discards that half of the space.
Yep. It then draws a new, tighter ellipsoid around the remaining half, finds the new center, and queries the oracle again. The volume of your search space shrinks geometrically with every single cut.
And the oracle can make different types of cuts, right? Like deep cuts, central cuts.
Yes, depending on how far the center point is from the optimal region, the oracle might make a deep cut that slices away much more than half the volume.
That's incredibly efficient.
It is. It could even make parallel cuts, simultaneously slicing away the space on the outside of two parallel lines. However, while the ellipsoid method is brilliant, the presentation emphasizes that it isn't always the fastest tool in the shed.
Oh, really?
Yeah, the expert source contrasts it heavily with interior point methods, or IPM.
Okay, if they're both trying to find the bottom of the bowl, what makes IPM different than the ellipsoid's shrinking bubble?
IPM is really the modern industrial workhorse. Instead of drawing boxes around the answer from the outside like ellipsoid does, IPM starts inside the valid space and carves a direct path through the interior.
Sliding down the inside of the bowl.
Exactly. It smooths out the boundaries of the constraints with a barrier function so it can slide right down to the optimal point. If you have a clean problem where you can explicitly list every single constraint, IPM is breathtakingly fast.
So why use the ellipsoid method at all then?
Because the ellipsoid method is an oracle framework. It doesn't need to know all the constraints up front. If you have an astronomically massive problem with billions of constraints, so many that just writing them down would crash a computer's memory, IPM will fail.
Ah, because IPM needs to see the whole space.
Right. The ellipsoid oracle just looks at one center point at a time. It is uniquely capable of handling unimaginable scale.
But even with these methods, some problems are so sprawling, they still choke massive server farms. The presentation details a few ways engineers physically break the math down, like alternating minimization.
Yeah, alternating minimization is a mechanical divide and conquer strategy. Imagine a problem with two massive blocks of variables, x and y, that are just hopelessly tangled together.
Okay.
Instead of trying to solve them simultaneously, the algorithm completely freezes block y. It treats y as a constant.
Oh, and suddenly solving for x is trivial.
Exactly. And once x is optimized, it freezes x and optimizes y. It alternates back and forth, just walking down the steps to the bottom of the bowl.
It's exactly like trying to solve a Rubik's Cube by just focusing on getting the top corners right first, locking them in, and then manipulating the edges.
That's a great way to visualize it.
Mhm.
The source also details dual decomposition, which actually distributes the math across multiple physical computers using a master-slave architecture.
How does that work?
Well, the master computer broadcasts a dual variable acting, essentially like a price to hundreds of slave nodes. The slave nodes independently optimize their small piece of the problem based on that price and report back.
Oh, wow.
Then the master adjusts the price based on demand and broadcasts again.
It's literally an artificial economy running inside the server to find the optimum. And they use techniques like ADMM, alternating direction method of multipliers, to add quadratic penalties to those prices, which prevents the artificial economy from wildly fluctuating, right?
Exactly. It acts as a dampener, essentially guaranteeing the distributed computers eventually agree on the optimal solution.
All right, all of this, the perspective transformations, the oracles, the master slave server knows, it's incredibly elegant theory. But what does this actually mean for the listener? Like, where does an ellipsoid oracle physically touch our reality?
If we connect this to the bigger picture, all of this mathematical programming culminates in electronic design automation, or ED. Yeah, EDA is the hyper-precise engineering discipline used to physically design and manufacture the microchips running our world. Without convex optimization, the modern computing hardware simply could not be built.
Let's look at a specific example from the source. CMOS inverter transistor sizing. How does the math translate to the silicon?
Well, in simple terms, an inverter is the most basic building block of a digital chip. It's the physical gate that flips a 1 to a 0. But physically, that gate takes up microscopic space on the silicon, and it inherently leaks power.
So they need to optimize it.
Right. Engineers use geometric programming, that log sum X trick we discussed earlier, to write an equation where the objective is to shrink the physical footprint of the transistor to the absolute minimum, constrained strictly by the maximum allowable delay in the signal.
And by transforming that layout into a convex problem, they guarantee they're printing the most efficient possible physical chip.
Exactly.
They also mentioned using those linear matrix inequalities for op-amp stability.
Yeah, operational amplifiers boost signals in everything from audio gear to medical sensors. If an amplifier is mathematically unstable, it creates a feedback loop and oscillates wildly.
That sounds bad.
Very bad. So engineers stack the physical tolerances of the amplifier into an LMI, which mathematically guarantees the hardware will not rip itself apart under stress.
The most brilliant application, in my opinion, was the design of FIR filters. Finite impulse response filters are what clean up the digital signals for your Wi-Fi or your wireless headphones.
Oh, absolutely.
But the physical constraints of tuning those radio frequencies, the magnitude limits, are wildly non-convex.
They're deeply non-convex. If you try to map a filter's magnitude directly, you end up with overlapping signals, dropped packets, and just terrible Wi-Fi. The space is way too messy to optimize.
So what's the workaround?
Engineers use a technique called spectral factorization. Instead of looking at the messy magnitude of the wave, they look at its autocorrelation coefficients.
Which shifts the perspective entirely.
Yes. It translates the problem from analyzing the messy shape of a wave into analyzing the linear algebraic relationship of the signal compared to itself.
That's wild.
It is. By optimizing the autocorrelation, the constraints become perfectly linear. They literally transform the foggy mountain of signal noise into a smooth, solvable bowl, guaranteeing your Wi-Fi connects without interference.
And the craziest part is that engineers aren't doing this by hand on massive chalkboards. The source notes that the ecosystem has evolved to automate these complex transformations entirely.
Oh yeah, nobody is doing this by hand anymore.
Tools like Python's CVXPY package allow an engineer to just model the chip's physical limits, and the software automatically figures out the monotonic transformations. Specialized cutting plane tools, like Alaugo, implement the ellipsoid method silently in the background. The algorithms do the heavy lifting so the engineers can just focus on inventing the future.
It is just a profound stack of computational leverage.
So, to trace the journey we've taken today, we started with a wildly complex world of non-convex physical realities. We learned that mathematical convexity is the golden ticket, a geometric space where the local valley is always the absolute global bottom. When the physical world refuses to be convex, we use perspective transformations and logarithms to bend the space until it complies. Algorithms like the ellipsoid oracle and interior point workhorses slice through millions of variables to find that bottom, and the result is the perfectly optimized silicon architecture that allows you to listen to this audio right now.
The theory translates perfectly into physical reality.
Uh,
But reviewing these sources left me with a rather provocative question.
oh,
Yeah, we've seen how engineers use spectral factorization and variable transformation to force messy, non convex physical realities into beautiful, solvable, mathematically perfect models. It makes you wonder, is it possible that one day we could apply these same transformations to highly subjective, non convex human systems? Could we map out a mathematical global minimum for complex social structures or global economic policies?
mm,
Or are human variables, by their very nature, fundamentally immune to being smoothed out by an algorithm?
wow. That is a question that will keep you up at night. Are human dynamics just non convex equations waiting for the right perspective transformation?
It's definitely something to chew on.
Well, on that note, thank you for joining us for this deep dive. We hope you'll keep questioning the underlying math of the world around you. Next time you're stuck on a seemingly impossible problem, just ask yourself, are you wandering the mountain? Or can you find a way to drop the marble in the bowl? Catch you next time.